Hello, everybody, and welcome back. We are now in chapter 17. Remember, in this week, we have multiple chapters because the sections are shorter. We're looking at when intuition differs from relative frequency. We're going to go through a couple interesting examples. But as always, we like to start with our thought questions. Do you think it is likely that anyone will ever win the state lottery twice in a lifetime? We know that in general, one person winning the lottery is not a likely event. So, one person winning the lottery twice, any one particular person, does not seem like a likely event. But we're looking at anybody in their lifetime, not just one specific person, the entire population. So, when we consider that and consider the relative frequency, the number of people that are actually buying lottery tickets day after day, assuming that if you win once, you continue to buy, we're going to see that it is actually likely that people win the lottery more than one time in their lifetime, that somebody will. In fact, we've seen it in the news that people have before won the lottery more than once. There are multiple people that have won over $1 million multiple times playing the lottery. How many people do you think you will need to be in a group in order to have at least a 50% certainty that two of them will share a birthday? Well, there's 365 days in a year. I don't need 365 people. I don't even need half of that. We're going to actually do the calculation coming up, but it's a lot fewer people than you may think. You test positive for a rare disease. Your original chances of having the disease are only 1 in 1,000. The test has a 10% false positive rate and a 10% false negative rate. We know what these mean, right? A false positive, the test comes back, returns positive, but you're actually disease free. False negative, the test says that you are disease free, but you actually have it. Whether you have the disease or not, the test is 90% likely to give you the correct answer. Given that you have been tested positive, what do you think the probability would be that you actually have the disease? Given that you've tested positive, what do I think that the probability is that I have the disease? So we're going to see here that the order of this is very important. The probability that any person walking on the street has this disease is 1 in 1,000. But I'm saying that you've already been tested and you tested positive. What is the probability that you then have the disease? Consider what the probabilities are for false positives and false negatives. We'll get into this further. If you were to flip a fair coin 6 times, which sequence seems the most likely? So by sequence, I'm saying that you have to have these results in order. Which of these seems the most likely to you? This is where in class I would have people raise their hands. Who believes sequence 1, 2, or 3? But if we consider every time that I flip the coin, I either have a heads or a tails, and it's a fair coin, so I have a 1/2 probability of landing on heads, 1/2 probability of landing on tails. Both of these sequences in their particular orders are equally likely to occur. You're just as likely as to get 6 consecutive heads as you are 3 heads followed by 3 tails, or the middle sequence. All 3 of these are actually equally likely. One exercise that I like to do is called a tree diagram. So, as I'm explaining this, I'd like you to write on a piece of pencil and paper with a pencil and a piece of paper. Start with a single point, and then you're going to make 2 lines from this point. These 2 lines were the possibilities when I flipped the coin. I either had a heads or a tails. From each of these outcomes from heads and tails, When I flip my second coin, I have two additional lines, heads and tails again. After just two coin flips, I see that I actually have four possibilities already. Heads, 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 tails, tails, heads, tails, tails. If we were to continue that exercise out further, we would see all of the possibilities if I flip a coin six times, and we would see that all of these options 1, 2, and 3 are all just occurring one time. Our final thought question: which would you choose in each set? Let's look at the first set. A gift of $240 guaranteed, or a 25% chance of $1,000 and a 75% chance of absolutely nothing. We are always going to assume here that our goal is to maximize our profit. So if the goal is to maximize the profit, which of these should we choose? We're going to get into the calculation coming up, but there is one correct answer. Let's look about C and D. A sure loss of $740, that would not be fun, or a 75% chance to lose $1,000 and a 25% chance to lose nothing. That chance to lose nothing does seem tempting, but is it the safer bet? We're going to discuss that answer towards the very end of this section. Our relative frequency interpretation. The relative frequency interpretation provides a precise answer to certain probability questions. As we saw in our probability chapter, chapter 14, we can determine the probability through repeated experiments. Anytime that I can repeat the experiment over and over again enough times that I can approach the true probability. Now it says often the physical situation lends itself to computing the relative frequency probability, but people ignore that. People go based on their intuition instead of looking at the actual data. So, are coincidences improbable? Let's take a look. A coincidence is a surprising concurrence of events perceived as meaningfully related with no apparent causal connection. So I'm assuming that these two are related in some way, even if there's no causal connection, such as winning the lottery twice. Let's take a look. In 1996, the New York Times wrote a story about Evelyn Marie Adams, who won the New Jersey State Lottery twice in a short time period. The New York Times claims that the odds of one person winning the top prize twice were about 1 in 17 trillion. But what's wrong with that? In the 1 in 17 trillion, this is the probability that one specific person will win the lottery exactly twice. Millions of people play the lottery. Some people buy 10 and 20 tickets a week. So it's not surprising that somebody somewhere would win the lottery more than once. In fact, statisticians Stephen Samuels and George McCabe calculated that you actually have at least a 1 in 30 chance of a double winner in a 4-month time period. It says, and better than even odds, that there would be at least one double winner in a 7th-month time period somewhere in the United States. So while it is very unlikely that one specific person will win the lottery multiple times, it's not improbable that somebody will at some point. We want to understand that distinction. Okay. Sharing the same birthday. How many people need to be in a room to assure that we have at least a 50% chance that two people have the same birthday? The answer is only 23. It's a very small value. So, We are going to assume that these are independent events, that one person having a birthday does not affect another person having a birthday. So let's find the probability that the one person has a set birthday. We'll say their birthday is August 10th, whatever birthday that we choose. What I'm now trying to do is to match to see if somebody else will have that same birthday. So it says the probability of the first three people all having different birthdays. Well, the probability the second person does not have to share a birthday with the first would be 364 any day but August 10th over 365. The third person cannot share a birthday with the August 10th, the person that we're trying to match, or the second person, which means that we have 2 days that we've already accounted for. So we're now down to 363 options out of our 365-day year. We can continue with this pattern all the way until I get to 23 people. So once I get to 23 people, I see that the decimal approximation is about 0.49. This 0.49 was the probability that nobody shared a birthday. Well, think about what we learned in chapter 14. If I have two possible outcomes, the sum of their probabilities must equal 1. So the probability that nobody shared a birthday plus the probability that at least one person shared a birthday would equal 1. So if I found the probability of none working backwards, we can now find the probability that at least 2 people share a birthday by simply subtracting. So if you have a room with 23 people in it, there's more than a 50% chance that 2 people share the same birthday. A lot smaller of a number than you may have expected. Most coincidences only seem improbable. So it says coincidences seem improbable only if we ask the probability of that specific event occurring to us at that time. So it's not improbable that it happens to somebody somewhere at some time. It's just highly unlikely that it happens to that one individual person at that specific time. That brings us to the gambler's fallacy, one of the more interesting topics in this section. The gambler's fallacy, people think that the long run frequency of an event should apply in the short term. So we discussed that law of large numbers as going back, as our relative frequency, as the number of trials increase, that relative frequency will approach the true probability. If I don't have enough trials, if I only flip a coin 3 times, that's not enough to tell me the probability of getting heads and tails. In the gambler's fallacy, people believe that the short run relative frequency should be the same as the long run. Okay. So it says, let's read this. It says, according to which people believe that even small samples are highly representative of the population from which they are drawn. In considering tosses of a coin for heads and tails, people regard the sequence heads, tails, heads, tails, tails, heads to be more likely than heads, 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 tails, tails, tails. We showed that during our first thought question that was not the case. So, independent events have no memory. This is a very important thing to understand. People tend to believe that a string of good luck in a casino will be followed by a string of bad luck. However, making 10 bad gambles in a row doesn't change the probability that we're going to make now 10 good gambles. Anybody here who is over 21 or has been to a casino before has seen thousands of people buy into the gambler's fallacy. Think of a roulette table. When you're at a roulette table, that is the game where you spin the ball and it tries to land on either red or black, and there's the two green spaces as well. If you have multiple reds in a row, people start lining up and betting heavy on red. Similarly, if you have multiple blacks in a row, people will start lining up and bet heavy that the ball will land on the black space. But those are independent events. Just because I landed on black the first time doesn't influence what I'm going to land on the second time. That's like saying I flipped a coin and got a heads. Because I got a heads, I think I'm now going to get another one. So it says the gambler's fallacy applies to independent events. It does not apply to situations where the knowledge of the outcome affects the probability. Now, we discussed examples like this in chapter 14. In card games using a single deck, the knowledge of which cards have already been played provides information about what is likely to be played next. So if I start with a deck of 52 cards, if I'm not putting the cards back into the deck, I'm changing the probability of what's likely to occur next. That's not the gambler's fallacy. The gambler's fallacy only deals with independent events, only events in which the probabilities are constant. Confusion of the inverse. Malignant or benign. It says a patient has a lump, and the physician assigns that there's a 1% chance that it's malignant. Mammograms are 80% accurate for malignant tumors and 90% accurate for benign tumors. The mammogram indicated that it was malignant. What are the chances that it's truly malignant? It's only a 7.5% chance. Why were the physicians making such a large mistake thinking that it's 75%? The physicians were confusing the probability of cancer given that they had a positive mammogram with the inverse, which is what we were looking at. They had a positive mammogram, so what's the probability that the patient actually has cancer? So we have to consider that confusion of the inverse. When we were looking here, again, what are the chances that it's truly malignant? The mammogram indicates that the lump is malignant. So we're looking at the probability that the person has cancer given that they already had the positive mammogram. The physicians were looking at it in the opposite direction. Let's look at this hypothetical table. So in this hypothetical table, we have 100,000 women. And it says the probability of the mass being malignant is 1%. So let's take a look here. It says the test shows that it's malignant in 800. The test shows that it's benign in 9,900. Sorry, the test shows that it's benign in 200. We read that table wrong. The test is showing malignant in 800, benign in 200. Of those 1,000 people, all of them actually had a malignant mass. When we look at the test showing that it's malignant and it's actually benign, that was 9,900 people. That seems like a lot of people, but we're looking at a total of 99,000 people in this group that had a benign mass. So again, that's a 10% chance of that false negative? Sorry, 10% chance of the false positive, showing that you have the malignant mass when you don't. So again, if we look at the probability just based on our hypothetical table, it's about 7.5%. So this is, again, the confusion of the inverse. The probability of false positives. If the base rate for a disease is very low and the test for the disease is less than perfect, then there will be a relatively high probability that a positive test result is a false positive. So again, just to clarify that, if the base rate for the disease is low, so if we have a very low chance that somebody in the general population has it, and if the test for the disease is not perfect, meaning it's not 100%, then there's a high rate of false positives. So to determine the probability of a to determine the probability of a positive test result being accurate, let's look at these three things. First being the base rate. The base rate is the probability that you are likely to have the disease without knowledge of the test results. So this is the probability that a generic person walking down the street will have this disease. The sensitivity of the test, the proportion of people who correctly test positive when they have the symptoms. And then the specificity of the test, the proportion of people who correctly test negative. Once we have this, we can either make a hypothetical table or use Bayes' rule. As you know, this class is focused on non-computational, so this hypothetical table was enough for us to understand. Our first case study of the chapter, the streak shooting in basketball, real or illusion? I'm sure you, like I, miss basketball and miss sports in general. So, what we did was we generated a phony sequence of 21 shots. These shots were either makes or misses. And we showed 100 basketball fans. 65% thought a chance of a shooting streak was in fact, 65% thought a chance of a shooting sequence was in fact a streak shooting. Streak shooting meaning that if I'm going to make the shots, I'm going to make multiple shots in a row. If I'm going to miss shots, I'm going to miss multiple shots in a row. But these are independent events. If I consider taking 2 foul shots, the probability that I make the first one does not affect the probability that I make the second one. So this is, again, going into the gambler's fallacy. If we look at this and we go on the sequence, in our first sequence, of the 20 throws, 10 are different. In our second, 14 of the 20, or 70% of the shots, are different. So if I'm changing more often, that would be what? Less of a streak? So the first one would be less streaky, more making multiple and then missing multiple. But again, making a shot the first time doesn't affect what I'm going to do on the second time. Now, it says that our research does not tell us anything about sports in general, but it does suggest a generalization about people, namely that they tend to detect patterns where none exist. So if somebody makes 3 foul shots in a row, does that mean that they have a higher or lower chance to make the fourth? It's not affected. Just like the person at the roulette table betting on black. Just because I had a black 3 times in a row, that doesn't affect what that fourth outcome will be. Okay. And this brings us to our final thought question. So we have a nice scenario, scenario 1, and then we have a not so nice scenario in 2. In scenario 1, we had to choose either A or B. In scenario A, we were gifted $240 guaranteed. In scenario B, 25% chance of a $1,000 gift and a 75% chance of nothing. If our goal, again, is to always maximize our profit, maximize the amount that we're bringing back in, which would I choose? In order to find this, we take our expected value. Remember our expected value calculations. We multiply the outcome by the associated probability, and then we sum that for each of the outcomes. In example A, to find the expected value, well, there's a 100% chance that I would get $240. With example B, to find the expected value, there's a what? 25% chance that we make $1,000 and a 75% chance that we make nothing. That is a $250 expected value. Again, that expected value is my theoretical average. If I were to do this over and over and over again, what would I expect the average outcome to be? On average, you're better off with option B than option A. Now that we've done that, let's take a look at our next scenario. In option C, we have a sure loss of $740. So the expected value is negative $740. Not a fun scenario. Is option D better? We find the expected value again by multiplying the outcome by the associated probability. We have a 75% chance of losing negative $1,000. 10% chance of losing $1,000. But we have a 25% chance of losing nothing. If I do a quick calculation here, I see that I have a negative $750 expected loss. What is this telling me? On average, I'm better off with option C. On average, I'm better off guaranteeing a $740 loss than I am with the potential to lose $1,000. So you just had to find the expected values here. Again, we're always assuming that our goal is to maximize the amount of money that we're bringing in. So, if you were facing a choice with the following alternatives, what would we choose? Alternative A, we have a 1 in 1,000 chance of winning $5,000. And alternative B, a sure gain of $5. Let's calculate the expected value one more time. To find our expected value for A, we have a 1 in 1,000 of winning $5,000. This is a $5 sure gain. If I look at the additional options here, looks like we're missing option B. Let's say alternative B is a gain of $5. What would I choose? Well, it says the decision is similar to buying a lottery ticket. If I look here, the expected values for A and B were the same. So on average, I'm going to expect the same value. So this would be essentially dealer's choice. Similarly for C and D, if I were to calculate the expected values, on average, you're expected to lose, with my expected value calculation, you have a 1 in 1,000 chance of losing negative, or of losing $5,000. This is a negative $5 expected loss. So which one would I choose here? Well, when I'm deciding between A and B, I have the exact same expected outcome. $5 isn't going to change my life, but $5,000 may. I'd probably pick option A. When choosing between C and D, this again the exact same expected value in the long run, but having to lose $5,000 versus having to lose $5, I'd much rather forfeit the $5 initially. So I like this statement in the red. It says, if people made decisions solely on the basis of maximizing their expected dollars, they would not bet. So let's look at the British Open. The British Open is a famous golf tournament, probably the most difficult golf course in the world, and pretty typically unpredictable as far as who's going to win. It says if the odds were 50 to 1 for Jack Nicklaus, what that means is that we have two possible outcomes. Either we're going to gain $50 from our $1 bet, or we're going to lose our $1. The problem is when bookkeepers and casinos and so on make our betting lines, they don't necessarily do so fairly. If you were to have fair odds, the sum of the probabilities for all of the players should add up to 1 or 100%. Either the first guy will win, or the second, or the third, and so on. That should add to 100%. But of course, they have a built in advantage. They have a house advantage. Here, if we look at just some of the golfers that were listed, we're already at 127%. So they have a built in advantage here. So to go back to that red statement, if people made decisions solely on the basis of maximizing their profit or maximizing their dollars, they would not bet. So that is the end of chapter 17. Chapters 17 and 18 will be posted on Blackboard today. If anybody has any questions, please reach out to me. WebAssign is the best way to contact me. So reach out to me on WebAssign if you have any questions. The homework for these upcoming chapters is going to be posted online, and we're going to have our first quiz outside of the class posted as well. Good luck and stay safe, everybody.